Hi there. This video is going to explain the purpose of the transformer equivalent circuit and how it may analyze the transformer, particularly for the losses through a transformer, the core loss and the copper losses. In this circuit diagram here, RP is not a physical resistor. It's not an individual component. It's a representation of the resistance of the primary winding. Similar with RS, it's a representation of the resistance of the secondary winding. Any piece of wire, any coil is going to have a finite resistance. XP, XS, again, these are not physical coils or inductors. They're representation of the flux leakage through a transformer. Not all of the primary magnetic field flux will link with the secondary. That's physically impossible in a real transformer. So these component values here are representations. You can get very close to 100%, but it's construction related. Our transformer here is a core transformer. If you construct a transformer, say in a shell type, these values will reduce. XP and XS are very minimal, but they're there to represent that you cannot get 100% flux linkage from primary to secondary. RC, what is that? RC again is not a physical resistor. It's a representation of the heat loss in the core of the transformer through eddy currents and hysteresis. If you want to get zero core loss, RC going to zero, you can remove the metal core between the primary and the secondary, which is completely counterproductive because you then lose the transformer action. So in any real transformer, RC has got a finite value to represent the heat loss in the core. You can minimize RC by materials such as silicon steel in the core and by laminating the steel core to reduce eddy currents. However, what we can do by experiment is measure RP with an ohmmeter, measure RS with an ohmmeter, and get the value of the reactance, the primary reactance, XC, which is a physical component. Why? Because it represents the reactance of the primary core and plus the steel core in action. And we do that on no load. At the moment, we've got no load so that we can represent the magnetizing current and understand the core losses. So by experiment, what we can see here, if we switch these meters back on, what we have is we have 12.8 volts RMS going in. We have 10 milliamps. That is a magnetizing current. Why do we call it magnetizing current? Move this, excuse me. This current is simply there for the transformer action. It is defined by the reactance in the transformer equivalent circuit of XC. So XC will define the magnetizing current, which at the moment is 10 milliamps. From that, we can work out the value of XC. So what we've got is 12.8 volts RMS going into the primary. We've got 10 milliamps primary current, so we can work out in the primary circuit the opposition to current flow is 1280 ohms. Now, because that value is significantly higher than the resistance of the primary winding that we will measure shortly, then what we will say is essentially that Z value is dominated by the reactance of the primary coil plus the steel core. So we can say that the XC value is 1280 ohms. From that, if we rearrange XC equals 2 pi F L, we can work out L, capital L, which is the inductance of the primary winding plus the core, is 4 henries. So what we've got here is we've got 625 turns on the input, we've got 120 turns on the output, and the turns ratio is then 120 divided by 625, so we will have 12.8 volts times 0.192 volts coming out. So we can see there the yellow on the oscilloscope screen. If we actually look at the RMS value there, here it says 12.8 and we get 12.8 on the meter, so they validate each other. So we're using different pieces of equipment to get the RMS value going in, and they give us the same value. On the same scale, 5 volts per division, we can see that the voltage coming out is stepped down. Yeah, so it's significantly less. So how do we measure RP then? So what we then do is we switch everything off, disconnect the transformer, disconnect the transformer. So what we can do is we can now take a meter, we pull these apart, should have been done, and we change this to ohms. And what we do is we change it to ohms, we put the leads together and make sure the leads read 0 ohms or as close to 0.2. okay, so that's 0. So what we're going to do is the input coil is this side, take that away because we're not using it now. So the input coil here is, we measure the 625, and what we measure is 6.6, 6.5 ohms. If you subtract the 0.2 from the 0 in the leads, it's essentially 6.3 ohms. So that's a fairly high resistance for that coil. So why would the coil winding RP be quite high at 6 ohms? Well, we can see here, fairly thin wire, probably 1 mil wire. It's got 625 turns. The wire is thinner on the primary compared with the secondary because we want to get all the windings onto the same mechanical bobbin, the same mechanical footprint. So we can measure RP as being 6.3 ohms in our equivalent circuit. Similarly, we can measure RS. Which is 120 turns, and if we look here, move that out the way, we're getting a reading of 0.5 ohms. If we subtract even the 0.2, then we're down to 0.3 ohms. So that's a very small resistance for that winding. So why would that be very small? Essentially a scale factor of 10 below the primary winding. Well, we can see here it's using much thicker wire, probably 1.5 mil, and there's less turns as well. So the actual length of the wire is significantly less, and the cross-sectional area is significantly greater. Resistivity is the length divided by the cross-sectional area. So in our equivalent circuit, we go back to here. In our equivalent circuit, we've measured RP as 6.3 ohms, measured RS as 0.3, and measured XC is 1280 ohms. So what we've done here is analysed the primary winding, the secondary winding. We've got the magnetising current on no load. RP is the primary circuit resistance, RS is the secondary, XC is reactance of the primary, the coil and the core, and the values of XP and XS will be significantly less than XC, which is 1280 ohms. And also comparing RP and RS values for measurement with XC, we can see that they are significantly less. So if we have primary winding and a steel core, you can see it's laminated, the reactance is going to be upwards of 1000 ohms or so at least. If you do want zero core losses, remove the steel core, but that will completely mitigate the transformer action, and the only limiting factor in the primary circuit will be the RP. So you end up with a very high current in the primary, but you don't have any transformer action. So to summarize, we can measure RP and RS directly. They're not physical resistors, the representation of the winding. We can measure XC by experiment so that we can then get an analysis of the magnetizing current and the core losses. Core loss is dependent on the voltage going in, but it's independent of the current, independent of the load current here. So at the moment it's no load, so we can estimate the core loss. Core loss is independent of load, but copper losses are I squared R non-linear effect with load currents in here. So if you have high load currents, your copper losses will be significantly higher than the core losses. Core losses are constant with constant input voltage, but copper losses are non-linear. It's an exponential effect because it's I squared R. So the equivalent circuit is an effective analysis tool to work out exactly what your losses are through a particular transformer. Thank you for watching.